Thank you very much. Is the mic okay?
Yeah.
Awesome. And then the screen. Oh, fantastic. Since we kicked the conference off with anime, this is my recommendation for 2024. This is a picture of Frieren. However, I do want to give you a fair warning. Every episode left me with half a heavy heart. But it's a really, really fantastic show, so highly recommend it. Okay, so we are all at Systems Distributed. So obviously, all of us are interested in distributed systems in one way or another. But it's important to realize that today, every application is a distributed application, right? Think of mobile applications or think of cloud applications, think of microservices. The question is not if an application is distributed. The question is only to what extent an application is distributed. So today, distribution is a fundamental aspect of software engineering. So I began my career in the United States as an intern nearly 20 years ago in 2006. And that year was not only pivotal for my professional life as a software engineer in Silicon Valley, but also pivotal in the history of cloud computing. In March 2006, AWS launched S3, and in August, EC2. And since then, the number of cloud applications and therefore distributed applications has exploded. But within the last 2 years, within the last 2 decades, we did not only see a quantitative change, we also saw a qualitative change. We transitioned from long-lived resources that hosted short-lived executions to long-lived executions that are hosted on short-lived resources. This shift has enabled an unprecedented scalability and reliability, but it has also introduced daunting challenges in how we develop and operate distributed applications. So in the early 2000s, we dealt with short-lived executions hosted on long-lived resources. When I started, my team owned a set of virtual machines. These machines had names. They were named after airports on the West Coast. So SFO, LAX, SAN. I do not know why, that was before my time. But resource termination at that time was a rare and most importantly, it was an exceptional event. Right? And at the same time, applications were mostly CRUD applications. User interaction mapped directly to a database transaction, and from beginning to end, the execution was expected to conclude within hundreds of milliseconds. So the probability of an interruption was low. From the point of view of the application, continuity was all but guaranteed. Right? So developers wrote code with the assumption the code would run to completion, right? Without any interruption. And if it didn't, the database transaction would save the day. So that greatly simplified the development compared to today's distributed systems. So since the mid to late 2010s, we have shifted to long-lived executions that are hosted on short-lived resources. Right? These resources managed by orchestration platforms like Nomad or Kubernetes, so processes, containers, virtual machines, they come and go. Yet our executions, such as ordering food from DoorDash, taking a ride with Lyft, or managing our stays with Airbnb, they range from minutes to hours to days to weeks. So this introduces a fundamental requirement: coordination across time and space. Executions now spend the majority of their time suspended. They spend the majority of their time waiting on external events. An external event could either be a simple timer, a human action, or an entire subgraph of additional executions. And now the probability of an interruption borders on certainty. From the application's point of view, continuity is no longer guaranteed. And mobility, the ability to suspend, move, and resume an execution to different resources required. This is a stark contrast to the run-to-completion model of the past. Now, what stands out to me a lot is how this simple illustration already reveals the essential requirements of modern distributed applications. From just one diagram, we can analyze the makeup of long-lived execution and introduce some key terminology. A span represents the interval of an execution from start to suspension. Within this span, an execution performs its tasks, its side effects, until it reaches a point where the execution must await an external event. The continuation of a span represents what happens after the span, the rest of the computation. The continuation resumes once an awaited event occurs, restarting the cycle of span and continuation. This is called continuation enactment. This structure of span and continuation forms the backbone of how we manage long-lived executions in distributed systems. In essence, we must be able to suspend an execution on one resource and resume it on another. Now, this concept of breaking long-lived executions into short-lived executions that can be executed without any further interruptions is not new. The fundamental principle was first formalized in the 1987 paper Sagas by Hector Garcia Molina and Kenneth Salem. In one of my favorite articulations, Pat Helland applied this principle to modern applications in his 2009 paper, Building on Quicksand. By breaking up long-lived executions into idempotent short-lived executions, capturing state in between, ensuring the state is kept across failures, the long-lived execution can tolerate interruptions. This is the bedrock of modern applications and is known today as an event-driven architecture. A term that strikes fear into the hearts of even the most seasoned and brave software engineers. Why? Because, well, the operational characteristics, the scalability and reliability of event-driven applications, that's a hit. But unfortunately, the developer experience of event-driven applications, that's a swing and miss. And interestingly, the conversation around event-driven architecture, its advantages and disadvantages, predates distributed systems and goes back to concurrent systems and operating system design. In their seminal paper from 1979 on the duality of operating system structures, Lauer and Needham proved a fascinating duality. Any procedure-based systems can be transformed into an event-based system. And conversely, any event-based system can be transformed into a procedure-based system. So this duality suggests that at a fundamental level, the two approaches are equivalent in expressiveness. So now we have a choice. But then, what are the trade-offs of that choice? Why would we prefer one over the other? Well, in a procedure-based system, also called direct style, an application is composed of a sequence of statements. Sequence of statements we know as functions. Functions are the universal abstraction for computation, and they compose recursively. Even our largest systems are built from the smallest building blocks, functions. And functions call other functions in a simple linear flow of control. So functions are the quintessential programming model, the ideal developer experience. Procedure-based code, easy to write, easy to read, and in one word, just easy to comprehend. However, functions do not have the desired operational characteristics. True, function executions provide continuity within a single resource. Right? But functions do not provide mobility. A function execution is tied to the resource it was started on, and its lifetime is limited by the lifetime of the resource itself. Now, in contrast, in an event-based system, an application is composed of a set of event handlers. For each event, the developer defines an event handler, also called a callback, to drive the program to the next state. But since the main workflow from beginning to end is expressed in many unordered callback functions as opposed to one single function, the developer needs to manually maintain the control state of the workflow. And that problem is known as stack ripping, or more commonly as callback hell. Okay, and now because of this fragmented nature of event-based application, they are hard to write and hard to read. And there's no coherent entity that specifies a coherent control flow. So now we say that the behavior of the system emerges. That's a rather elegant way of admitting that we actually don't know what's going to happen next. So, however, callbacks do have the desired operational characteristics. Yeah? They don't have continuity, but they do provide mobility, allowing executions to continue on different resources. And now we have to make a choice between a delightful procedure-based experience or a desirable event-based characteristics. Or do we? Can we have both? Can we create a programming model that offers a delightful developer experience while still providing the desired operational characteristics? And once again, we will look not at distributed systems, but at concurrent systems. In 2006, the paper, A Language-Based Approach to Unifying Events and Threads, made a pivotal statement. We can have a procedure-based programming model on top of an event-based execution model. So in other terms, we can write code that looks and feels like traditional sequential procedures, yet that code executes in an event-driven manner, facilitated by an event loop. The event loop is a crucial component that bridges the gap between procedural code and event-driven code. Now, if we equate raising and handling an event with sending and receiving a message, we can already see how distributed systems are inherently event-driven systems. And in addition, if we are able to move executions, or more accurately, the continuation of an execution from one resource to another, we already have all the ingredients that we need to cook up scalable and reliable distributed systems. So now this is the story of distributed async await, a programming model that offers a delightful developer experience for building scalable and reliable distributed systems. Or, in other words, dead simple, durable executions. Now, distributed async await does fall into the category of durable executions, but stands apart as a different interpretation. And as a different interpretation, we are following a different philosophy on multiple dimensions. So, for example, other durable execution frameworks typically provide abstractions like workflows, a proprietary non-composable abstraction. In essence, a workflow is a sequence of steps, also called activities or actions. But since they are not necessarily composable, sometimes you have to plug a hole, and from there, the frameworks quickly snowball into an avalanche of additional abstraction like workflow chains, parent workflows, child workflows, local actions, remote actions, signals, side effects, transactions, communication services, and deployments. Yeah. And then in these frameworks, a workflow is a unit of failure tolerance, but it's not a unit of composition. And since workflows are non-composable, they may work well for a few clearly delineated entities of your system, but they struggle to be your system. And additionally, other durable execution frameworks typically impose operational restrictions. For example, requiring a fixed topology. Right? So most common other frameworks require a star-like topology, a set of workers connected to one central server. And while this looks straightforward, this results in a tightly coupled centralized architecture. And every step of the workflow requires communication with the server and a server-side scheduling decision. A constant back and forth, adding latency to your application and making the server a significant bottleneck, requiring a significant amount of resources. So with distributed async await, our company Resonate takes a different, almost opposite approach. At Resonate, we subscribe to the philosophy that perfection is achieved not when there is nothing else to add, but when there is nothing left to take away. And we call this philosophy dead simple. So for instance, instead of drowning you in an avalanche of proprietary non-composable primitives, Resonate provides an open composable programming model that is based on two universal abstractions. functions and promises. And instead of a fixed topology and a centralized architecture where every step requires a server interaction, Resonate provides a flexible topology and a decentralized architecture where you can decide how often, if at all, you want to interact with a server. Now, dead simple is not just a catchy phrase. Dead simple is at the center of our technical values. Dead simple to understand, dead simple to develop, and dead simple to operate. And this hinges on finding the right abstractions. Get this wrong, and then nothing will be achieved. But get this right, and everything falls into place. So what is our foundation? What is the foundation of distributed async await? Well, somewhat anticlimactic because it's already in the name. Distributed async await extends async await. Right? And it's based on the same abstractions, functions and promises. Two abstractions that are well liked and well understood. Functions and promises are composable, universal abstraction for computation and coordination. The building blocks of each and every system, distributed or not. Do some stuff, wait for some stuff. And when the caller invokes the callee, instead of waiting for a result, the caller immediately receives a promise, while the callee executes concurrently. Now the caller and callee are able to coordinate their execution with the caller waiting for the promise and the callee completing its promise. So again, in async await, when a caller invokes a callee, the caller does not transfer control to the callee. Instead, the caller receives a promise and resumes execution. The callee starts execution. And eventually, when the caller needs a result of the caller awaits the promise. If the promise is pending, the caller suspends until the callee terminates and completes the promise. And in async await, after the caller invokes the callee, there's more than one unit of execution. There is 2 units of execution. I see that, unfortunately, some colors are not making it to the screen. Okay. A promise has 2 facets. On the one hand, a promise can be interpreted as a representation of a future value. But on the other hand, a promise can be interpreted as a representation of an execution. But in any case, a promise is either pending or completed. More specifically, resolved or rejected. So if a promise is pending, the promise is unfulfilled, and the fulfilling execution is still ongoing. And if a promise is completed, the promise is fulfilled, the fulfilling execution has concluded. Resolved indicates success, and rejected indicates failure. Now, importantly, async await does not form a call stack, as there are multiple concurrent executions. More than one thing can run at a time. So instead, async await forms a async call graph. The call graph represents the concurrent structure of your application. When an async execution invokes another async execution, a promise is created, and a concurrent execution is spawned. The caller is then able to await the promise, in effect, awaiting the termination of the callee. And with these simple interactions, we can build arbitrarily complex, sprawling, concurrent yet coordinated computations. Awaiting a promise delineates an execution into multiple spans. And when an execution awaits a promise, the execution is suspended, and its continuation will be invoked when the promise completes. So this structure is already our very roadmap to distributed systems. So distributed async await extends async await and makes distribution and recovery a first-class citizen baked into the programming model. Async await formalizes the concurrent structure of local computations and just completely ignores recovery, does not concern itself with it. Behavior undefined. But then in contrast, distributed async await formalizes the concurrent structure of global computations and additionally formalizes recovery. So then, given what we know now about async await, what extension do we need to make? What do we need to add to make distribution and recovery a first-class citizen of the programming model? We need durable promises. And durable promises are, and here we go again, dead simple. A durable promise has a unique ID, a URL, and stores its state in durable storage, a database. That's it. That's all we need. This simple concept forms the very foundation of a distribution and recovery first programming model. No complex programming models, no complex machineries, only durable promises. Now let's take a closer look. Let's take a closer look at the distribution. Async await is a formalization of the local concurrent structure of your computation. This focus on local concurrency is crucial. Do we have a chance of dialing the colors? There is a background color that I cannot see. Can anybody see the background color? No. Okay. I have to go without. So this focus on local concurrency. Oh, yeah. Woo! Thank you. It happened. So the focus on local concurrency is crucial. Within a process, async await provides formal call semantics. But across processes, relationships are no longer formally handled by the runtime. Instead, they are managed ad hoc by the application developer. And the two popular choices, as we are all aware, are HTTP calls and job or task queues, each with their own drawback. HTTP calls tightly couple caller and callee. Right? The callee imposes its lifetime on the caller. Caller can't go anywhere. You have to hang on to this connection. Yeah? This is an odd relationship between two supposedly independent units of executions. But despite their drawbacks, HTTP calls are often developers' first choice because they're pretty easy to implement. Now, job or task queues loosely couple caller and callee. But then, after enqueuing a job, it disappears somewhere into the system. Right? Raising questions about completion results, failure propagation, and caller resumption. So coordination across processes becomes complex. We are left with fragmented call graphs, incomplete relationships, no value of failure propagation, limited debuggability, and little system insight. But with distributed async await, cross-process relationships are now first-class relationships. Instead of many fragmented call graphs, we have one coherent call graph with uniform control flow semantics, uniform data flow semantics, that is, uniform value propagation and uniform error propagation. So the boundaries between processes no longer create gaps in your programming model. This uniformity and coherence is what allows us to handle distribution and recovery seamlessly as an integral part of the programming model. Now let's take a closer look at recovery. The desire for durable execution came because long-lived executions outlive short-lived resources. So in effect, durable executions are executions with resume semantics. So an execution is a sequence of steps. And when the resource hosting the execution terminates, well, the execution terminates. Resume semantics refer to the ability of an execution to continue execution from its interruption point when another resource becomes available. Okay, but on first glance, resume semantics feel a little bit like voodoo and black magic, right? A dead execution coming back to life. But resume semantics are surprisingly easy to achieve. Once again, they're actually dead simple, based on restart semantics and idempotent steps. So the core idea hinges on an equivalence relationship. The effect of an execution that is interrupted and resumed is equivalent to the effect of an execution that is interrupted and restarted, given the individual steps are idempotent. And this equivalence is the foundation to recovery with resume semantics in distributed systems. Now let's move on from theory to practice, to develop an intuition for the use and the mechanics of distributed async await. So we look at a few examples. First, the quote-unquote transactional semantics. I know there's a very database-heavy crowd, so don't yell at me. Quote-unquote transactional use cases. So this function illustrates purchasing a digital asset. For example, a song or a video. First we charge the user's credit card, and next we grant access to the asset. So for this transaction to be correct, both steps must execute to completion. Right? It's not cool if the execution only charges the credit card, but then doesn't grant access to the asset. So let's walk through an execution of our purchase function. When we call resonate.run distributed async await's entry point, resonate first creates a pending top-level durable promise. This promise includes information about the function that was called and its parameters. Then we invoke the charge function. Here we are using Resonate's low-level API to highlight that this is a local function call. Resonate creates a durable promise and invokes the charge function locally. Then we await the completion of the durable promise, in effect the completion of the local function execution. Okay, and then next we invoke the access function. Resonate creates a second durable promise and invokes the access function locally. And then we await the completion of the durable promise and in effect again the completion of the local function execution. And finally we complete the top-level durable promise. The completion of the top-level durable promise signifies a successful conclusion of the purchase. By completing this promise, we're indicating that all steps of our transaction have been executed successfully. Okay, now let's explore the control and data flow in case of a failure. So the purchase function, again, execution follows the same path, right, as the previous example. So the top-level promise is created. The first intermediary promise is created and completed. Then the second intermediary promise is created. But then during the execution of access, somewhere during the execution of access, the process crashes. So how does Resonate recover from this situation? It's actually pretty straightforward. The key to recovery just lies in the top-level promise. The top-level promise contains the request. That is, all the information about the invocation of the purchase, including its parameter. All I have to do is ask the system for pending purchase promises to know what I need to recover. And with this information preserved, Resonate can simply restart the execution when a process becomes available. Now in recovery, we handle processes based on their state. Since a promise representing the charge function execution is already completed, we don't need to execute the charge function again. We can simply return the previously recorded value that is persisted in the durable promise. However, the promise representing the access function execution is created, but it is still pending. So we must execute the access function again. However, that scenario highlights a crucial requirement. Functions must be idempotent. We don't know where that thing crashed, before it granted access or after it granted access. There is an uncertainty interval between creating a promise and completing a promise. If a promise is created but not completed, we can't be sure if the intended side effect has occurred. We must retry the function, therefore the function must be idempotent. And then we await the completion of the function execution, therefore the completion of the promise. And once that is done, we complete the top-level durable promise. And then this final step signifies the successful recovery and completion of the purchase transaction, despite an earlier failure. And this scenario demonstrates how distributed async await achieves completeness even when interruptions occur. But that does raise a really interesting question. Since every function must be idempotent already, why are we creating intermediary promises? Creating an intermediary promise is necessary if an execution is very expensive or takes a long time. However, in our example, charging a credit card is not computationally expensive, and granting access to a digital asset is not very long running. So in this case, we don't actually need the overhead of creating intermediary promises. So we can optimize this process. Resonate offers flexibility in configuring when durable promises are created during the execution. Right? And in this case, we only create the top-level promise. Since this promise includes all the information about the invocation itself, giving us enough to restart if a failure occurs. Since the individual functions are fast-paced and idempotent, no problem if we actually execute them again. So during this execution, we won't create any intermediary promises. And this approach still achieves the failure tolerance while avoiding unnecessary server interactions. So this is a great example of how distributed async await allows you to fine-tune the balance between durability and latency in your distributed system. So let's move on to our second example. This example is more contrived, but it is more thought-provoking and demonstrates a crucial aspect of Resonate. Its foundation on recursively composable abstractions. So this example demonstrates recursion. Granted, calculating a factorial isn't the canonical use case for concurrency or distribution. However, it is the canonical use case for demonstrating recursion, so we roll with it. So in this case, the factorial invokes itself locally. That is significant because it shows that in distributed async await, there is no separate concept of workflow and actions or workflow and activities. There are only functions and promises. Even the largest systems composed recursively of the smallest building blocks. Now, by default, we created a durable promise for each invocation, but we can actually trade durability for latency. So in this example, we create a durable promise every 10th step. So therefore, if the execution crashes after 1,999 steps, we only need to redo 9 steps. Now, if the execution crashes after 1,999 steps, we have to redo 99 steps. And now, if the execution crashes after 1,999 steps, we have to redo 999 steps. But in addition, Resonate doesn't only give you control over the recovery, but also over the distribution. So we are calling the factorial locally. Let's get a little bit more adventurous and call it on a different process. So in this example, instead of calculating the factorial locally, we calculate the factorial remotely with every single step of the calculation, scheduled by the global event loop, possible every single step executing on a different process. And again, we can get a little bit more creative here, executing 9 executions locally, and then on every 10th execution, hop over to a different process. Again, a little bit more contrived, but still a cool example. All right, and now the last one. That's my absolute favorite example. Let's build a simple application, a countdown timer. We initiate a countdown with a phone number, a count, and a frequency. So for instance, we might initiate a countdown starting at 10 with a frequency of 15 minutes. The application will send a text message to the provided phone number every 15 minutes, decreasing the count by 1 each time until we reach 0. Now we know what a countdown is. So let's build this application on a serverless platform using functions as a service. First, let's build this application the most straightforward way, the procedure-based way. So this function will send the current countdown value and then wait for the specified delay in a loop. This is a delightful developer experience. Code is easy to write, easy to read, and directly reflects our business logic. As software developers, we don't even need to think about the state of an execution, managing instruction pointers, stack, heap. All of that just happens. So there's one execution on a logical layer carried out by exactly one execution on the physical layer, using a single function instance. So both the logical layer as well as the physical layer consist of one execution with identity and integrity. However, as we are all aware, there are many problems with this approach, both in the absence of failure and in the presence of failure. So a countdown starting at 10 with a frequency of 15 minutes will take 135 minutes or 2 hours and 15 minutes. Nobody check the math. To complete. So performing a back of the envelope calculation, again, nobody check the math, assuming that a message takes about 500 milliseconds with an API like Twilio, the execution is active for 5 seconds and asleep for 2 hours, 15 minutes, and 55 seconds. Yeah, unfortunately, often serverless platforms have a time limit. So for example, AWS Lambda has a time limit of 15 minutes. So if your function execution exceeds that time limit, it will forcibly be terminated. But even if your platform does not have a time limit, you are paying for 2 hours and 15 minutes instead of 5 seconds. And in this example, we were exasperating the problem with an HTTP binding. HTTP works over TCP, which calls itself fanciful a stateful connection. If the connection drops, your function executions will be cancelled. So now we are forcing the client to hold an active connection for 2 hours and 15 minutes to make sure that the process executes and we know when the process completes. And in case of a failure, this bad situation becomes worse because when we restart the process, we basically restart from the beginning. Right? So, and again, we're exasperating the problem with the HTTP binding. If that execution experiences a crash, the client has to stick around to restart. The client is in a supervising role. Okay, now let's write this application to circumvent forcible termination due to timeouts, and we use an event-based approach. So this function sends the current countdown value and then schedules another invocation, a self-invocation for the future. This is not a delightful experience. The code is not easy to write, it's not easy to read, and only indirectly in a very roundabout way reflects our business logic. Now imagine a few loops and if statements and try catch handlers. Managing that in an event-driven fashion is not at all that simple. So now as software developers, we need to manage the state of the execution explicitly on an application level. In effect, we manage the instruction pointer, the relevant section of the stack, and the relevant section of the heap. And this one-off implementation works well with sleep, but what about other events? Invoking and awaiting concurrent executions, implementing a fork join model, or waiting for user input. Simply scheduling a message on a message queue does not support these interactions. Now there's still one execution on the logical layer, but now carried out by many executions on the physical layer. So on the physical layer, the execution lost identity and integrity and is instead fragmented into multiple executions across multiple processes. But we did improve on a multitude of problems. We will not run into any time limits. We will only pay for active time, not idle time. A crash of an execution does not result in a complete restart, but only into a restart of the execution thanks to at least one's delivery guarantees of a queue. So now the caller is no longer the supervisor. Redelivery semantics of the queue are the supervisor. But we are facing other problems that we didn't have before. So now there is no longer a handle to the execution. In fact, most of the time, 2 hours, 14 minutes, and 55 seconds, the execution exists as a message scheduled for delivery in the future on some message queue. So I cannot ask the system to enumerate all running processes, whether active or idle, and without a handle, we cannot cancel the execution or wait for the execution to finish to do something else afterwards. Right? So out of the frying pan, right into the fire. Now, if we write this application with distributed async await, the code looks procedure-based, but executes in an event-based manner. Thanks to the durability of durable promises, the application can voluntarily terminate on await and resume after a delay. So now we get the best of both worlds. Now it looks like this and executes like that. Okay, now finally, I want to take this opportunity, speaking at Systems Distributed, to share some personal news with everybody. So last year, I set out to write a book about distributed systems. So starting in January, I wrote 1 chapter per month. And then in December, I completed and released the first edition of Thinking in Distributed Systems, so self-published. So now I'm super excited to announce that Manning Publishing has chosen my book for publishing and distribution. So as of today, Think in Distributed Systems is available online via the Manning Early Access Program and will be available in print later this year. Well, thank you.